Now today I'm going to talk about the continuous view of the universe as opposed to the digital or numerical view of the universe. And if it's a bit heavy going, then maybe you shouldn't listen to this. It's going to be slightly philosophical, slightly mathematical, so it may not be your cup of tea, as they say. But one of the interesting things, when I was doing quantum physics, I came up with the solution to the entanglement problem in quantum physics, and the only solution I could see that explained it was the digital solution, that the entangled particles were actually being controlled algorithmically in a von Neumann or computer-like way. But when I come to that conclusion, I thought, well, if it's true for entangled particles, it must be true for every particle. And then I kind of hit a brick wall, and I thought, my goodness, I'm going to have to look at some of the earliest philosophies, because I had to look at the earliest philosophies. What did human beings think the universe really was when you go back 5,000 or 6,000 years, or as far back as I could possibly go? Unfortunately, the Vedic literature on this is missing, but I strongly believe that they'd actually worked a lot more out than we believe. But one of the paradoxes or early problems that made us go along the wrong direction was, in terms of continuous and digital, was Zeno's paradox. That's Xeno. And he was a Greek philosopher, I think about 500 BC, something like that. I'm not sure of the exact date. But he was the most amazing philosopher that came up with amazing paradoxes. And I'm going to try and just explain to you verbally one of the paradoxes. It'll test my powers of explanation, this. But Zeno's paradox is, one of them is saying things cannot move. Now, he explained this by drawing a picture of an arrow. Imagine an arrow flying through the air. So he drew a picture of the arrow at one instant of time, which, as you can imagine, on a piece of white paper would just be a picture of an arrow. And he said that this is an arrow at an instant of time. And then he went on to say, in an instant of time, the arrow doesn't move, because we're actually saying that the instant is an infinitely thin line in time. It's at one particular time is an instant, isn't it? It's not a range of times. An instant is not from 1 second to 5 seconds. An instant is exactly 1.0000 forever seconds. And he said that an arrow cannot move in an instant of time. But the motion of an arrow is made up of the addition of instants of time. Now, this is a philosophical nonsense, because if an arrow cannot move in one instant of time, then how can it move at all? Because the sum of motion is the sum of instants, but in no instant can an arrow move. So it's a philosophical contradiction. It's a paradox. He was, of course, rubbished in the kind of Greek parliament of the day by some old Greek philosopher standing up, walking across the room and saying, well, what am I doing? I'm moving, aren't I? I'm walking. And then everybody laughed, and Zeno was made to look a bit stupid, because he'd actually proved that by walking you can move. But let's think again. I mean, it was Zeno's paradox and this guy walking across the room that I believe set us on the path of continuous line-like view of the universe, curves and lines. But whereas in fact the truth is, it's numerical. Let's go to the crux of this paradox. Why can't an arrow move in an instant of time? It's because you're saying that an instant of time is 1.0000 forever, then that is true, it can't possibly move. But you could say, well, it can move just a little bit from 1.01 to 1.02. That's where the movement takes place. But it's not actually true, because if you go right back to as small as you can possibly get, at some point a number has to go from 1 to 2 for that arrow to move. If however small that number is, it could be 1.0001 to 1.0002, but at some instant or some point along that line, that the change must be from one number to another number. And then kind of I regard as crazy philosophers said, well, this in the limit time tends to 0, this enables the arrow to move. But think again, I don't think it's true. At some point the arrow must jump from one number to another. If it doesn't jump, then you must assume that the universe is lines that go down to 0. But what possible proof have we got that the measurement of something goes down to 0? All the evidence suggests that it doesn't. And for example, quantum theory limits the length to about a Planck. There's absolutely nothing below a Planck's length, you could say. Excuse me. A quantum jump from energy is from one orbit to another. It doesn't go 1, 1.5, 2. It goes from 1 to 2. It's a jump from one energy to another. And this to me is evidence that the universe is actually a digital universe and not a continuous universe. And Zeno was in fact right. At some point the arrow is actually, what it's actually doing is jumping from one point to another. Now this ties in with a computer program absolutely perfectly. If you watch a ball in a computer game, it seems to be moving slowly, but I can assure you that in fact and in truth, and absolutely true, it's not moving continuously. It's jumping from one coordinate to another on the screen, because the algorithm makes a ball move is x plus 1, x plus 1, x plus 1. Every tick of the computer clock will move the ball forward by 1 unit, but it's not continuous. It's certainly not continuous. It jumps from one point and then stays there for a little while and jumps to another point, stays there a little while. Also, it can't move faster than the computer clock ticks, and that has a parallel to the speed of light. The speed of light is the speed of ticking of the universe. The speed of something cannot possibly be greater than that, because like the computer clock in the universe, it would have to go faster than that. In a computer, a ball can't possibly go faster than the tick of the computer clock. It can only, that's its maximum speed. So we can see from this piece of thinking that Zeno's paradox was indeed a paradox, and I wish they had taken it more seriously and not just discarded the idea of numbers getting so small that they go to 0, where the universe, philosophically, it can't do that. If you will examine other philosophers whereby that is a slightly improbable event, that everything goes down to absolute 0 with no jumps. So that's one bit of evidence that Zeno was in fact correct, that the movement of anything is actually a series of jumps from one number to another. However small, it may look continuous, but what is happening is whatever object you've got is jumping from one location, staying there for a little while, and then jumping to another. And so, in fact, nothing moves continuously, we should say. Continuous movement is not possible. And this old philosopher that walked across the room ridiculing Zeno, if we could expand time like by billions and billions, we'd actually see he was jumping from one spot to the other as he walked across the room. So